Welcome everybody. We are happy to have with us today Elimelech. Kehn is currently a postdoc at Rice University, working with Lydia Kavraki and Moshe Vardi. I can tell you that Lydia's group is one of the leading groups in robot algorithms in the world. Prior to that, Kehn was in a special autonomous robots program, PhD program in the Technion, working with Vadim Indelman. Kehn won prizes for his PhD, for his postdoc work. He is also active in various university communities. And he will tell us about scaling up planning for long-lived autonomous robots. Please.
Thank you, Daniel. Hello, everyone. I'm very happy to be here. My name is Kehn, but just FYI, around the world, people usually call me Kehn. So if you talk about Kehn with someone, then that's today I'm going to provide an overview of my academic research for my PhD, for my postdoc, that aims to benefit autonomous robots by allowing them to plan at high scale. So these are some of the autonomous robots that we might be familiar with today. We have robots in factories like these robotic arms. We have the very popular Roomba vacuum cleaners. We start seeing on the roads some autonomous cars and some robots for exploration of hard-to-reach environments. But looking at all of these tasks or all of these examples, they're quite mundane, the tasks that they're trying to solve. But when we envision the robots of the future, we might think of something that looks like this. Right? This is the robots that we actually want to have around us. Right? They are long-lived, and then they operate for long periods of time. They can solve different problems. They are multi-purpose. They can robustly overcome different tasks, different challenges, and maybe we want them to improve and adapt over time, just like humans do. So all this encapsulates a little bit of a spark of robotic cognition that we want to start seeing in this robot. And one of the challenges that we need to overcome to go from the robot in the previous slides to this robot is allowing them to plan at high scale. What is planning? Planning is a part of the autonomy paradigm, is the key component of autonomy. We have this paradigm, which usually is comprised of plan, meaning deciding which actions we want to perform next. Act, meaning I execute these actions. Sense, which encapsulates state inference, meaning I try to understand after performing the actions where I ended up. Right? And then we go around again. And planning at high scale, meaning that we want to solve hard planning problems. For example, they can have long horizons. So I need to perform a lot of actions until I complete the task. It might have uncertainty. It might complicate things. I might have a robot that has a lot of degrees of freedom. So these are examples of high scale. So with my work, I will mainly focus on planning, and we'll see different formulations of planning problems, and we'll try to benefit them and try to make them scale solution algorithms scale better in order to learn. So we have two main portions of this talk. One of them will cover my PhD research, in which we'll focus on the problem of navigation in an unknown environment, and we'll see some contributions to it. I'm not sure that I'll have time to go over all of them, but we'll focus on one of them at least. In the second part, we'll talk about two other robotic planning problems. So planning in robotics has many different flavors, and it is formulated in different ways. So each one of these problems will be a different formulation that I will first introduce, and we'll see the contribution to this specific formulation of what is our approach to solve this problem more efficiently. Okay, so let's dive into the first problem, which is navigation in unknown environment. So we can see here a mobile robot. It navigates in this indoor environment. It has some features in it, like this plant and this lamp. Usually we call them landmarks in the environment. The robot has a sensor, so it can sense this features as it navigates, and it can also execute control actions that will make it move around the environment. And the only thing that we assume is that we have the models of the robot, so the controller model that tells us what happens after I execute an action. And the sensor model, for example, if it's a radar, it will tell me what's the distance between the robot and its landmark, or if it's a camera, it will provide the image. And these are known with some added noise. So now the planning problem here is after the robot moved around the environment a little bit, we try to choose what trajectory to follow next. And do so autonomously. So we narrow down this problem a little bit just for the sake of this talk to perform this decision problem, given the robot's knowledge on the world and some collection of candidate trajectories that you might take, you want to choose the most informative trajectory. And before we can actually solve this problem, we need to clarify what these two terms mean. So first, let's try to understand what the robot knowledge on the world means. So the robot, I don't know if you can see the colors. Do you want to turn off the lights? The robot doesn't exactly know its location in the environment or the landmark's location in the environment. It only knows the history of sensor measurement and actions that it executed, which you can see here. For example, if we have this link here, it means that the robot saw this landmark at this point, and if these two poses is where the robot is. If these two poses are connected, it means that the robot moved from here to here. So that's all that we know. And given this knowledge, we want to try to estimate the location of the robot and the landmark. Okay, and this estimation problem is known as simultaneous localization and mapping, or SLAM in short. And planning after solving the estimation problem is known as active SLAM. So before we can talk about active SLAM, we first need to understand what SLAM means. Which again, SLAM.
A question about the knowledge, which
Yeah.
So once the robot, so if I understand correctly, the robot has been there, like in the leftmost point, and then you observed the, say, plant. So in what sense the robot doesn't know the location of the plant?
So this measurement has some noise.
So in the sense of the noise.
Yeah, so it has noise in this measurement, and also as it executes an action, it only knows its new location with some noise. So over time, this drift accumulates, and we don't know exactly where it might be. We just know where roughly we try to estimate where we might be.
Okay.
Right, and we can see here maybe that we've observed this plant from two different locations. So they might not overlap exactly, and we can exactly what it's most likely to be.
But also the observation of the plant has been also throughout the entire path from point A to point B, right? Not only in these two locations.
So I'll talk about it in the next slide. I'll clarify.
Is there an assumption that these electrons will not move over time?
For the sake of this discussion, yes, we can assume that they are static.
Yeah, so the task here is just exploration. The robot doesn't have any specific task that should execute. Like
So I will talk about it also.
okay.
I have a lot of things to cover. It started a little bit late, so I'm trying to run through it. So we can always talk. If it's a very important question, then yes, stop me. But if it's want me to elaborate, we can just. All right, so we want to solve this problem, which is known as active SLAM. First, we'll talk about SLAM. Brief some background. SLAM is a very fundamental problem in robotics. Every robot that moves around and uses sensors to try to locate itself uses some version of SLAM. So autonomous cars, vacuum cleaners, rovers on Mars. Right? Usually we used to solve this problem using filtering, like Kehn filtering, but recent approach use graph theory or graph-based formulations, which allow us to have much more accurate estimation, but it's also much more computationally demanding because this graph grows over time. And this is an open problem in robotics now, how to perform efficiently active SLAM using the graph-based approaches. And one of the open questions is how to find effective representations for this problem, which we will talk about later. So again, we'll go back to SLAM. This probably solved iteratively over time as the robot navigates. It keeps updating the estimation. And we assume here that the robot trajectory is discretized to a sequence of poses. So then we can reason about the observation at every given pose. And the sequence of poses together with the landmarks give us the state vector, which is what we want to estimate. Okay, so given this entire history of operation, of observations and actions that we've performed, we can reason about the belief. Belief is simply the probability distribution over the state vector given the history. Right? And this belief is what conveys the knowledge of the robot on the world, which we will use to plan. So with some very basic math, we can factorize this belief to just the multiplication of all the models that we had before. And given this factorization, we can just depict the factorization, the belief over a graph. So this is what we call the factor graph. We have here variable nodes that corresponds to the robot poses, and this landmark nodes corresponds to the location of the landmarks, and they are connected with these factors, with these constraints that tells us if there was an observation here or there was if it's two consecutive poses. All right, so again, the knowledge of the robot is encapsulated in the belief, which is represented with the graph. And given some very basic assumptions of Gaussian noise and that we can linearize the models, this factor graph can be represented with a matrix, which we call it the Jacobian matrix. And here, every column here corresponds to one of the state variables, and every row here corresponds to one of the constraints. So if I have here a non-zero element, it means that this variable is involved in the constraint. So for example, we can see here, I don't know if I should use this, if I should go here, if I should go use this for people on Zoom. So improvise here. So we can see here that the last line corresponds to, we have non-zero elements of X3 and L3. So this corresponds to this constraint here. This line here would have non-zeros at X2 and X3. So this is this constraint here. So this matrix represents the graph. But in fact, we don't reason about this matrix as it is. We reason about the matrix in its upper triangular form. So this is what we call the square root matrix of this matrix. It is just given by applying the QR factorization that makes it triangular, upper triangular. And this formulation allows us to find the best estimate and understand the uncertainty and so on. The bottom line of all this discussion is that the knowledge of the robot is encapsulated with this upper triangular. Okay. If you've lost me, this is the bottom of the picture. And one of the advantages of this matrix is if we have a new factor, like we have here a new constraint, which corresponds to a new row, we can just add it here to the bottom and stick it to the bottom and retriangulate the matrix incrementally. So we don't have to calculate the entire matrix from scratch, but we just need to here take this block and update. Okay, so this is the first non-zero column, the first involved variables, define which part they need to. Okay, so now that we understand what the robot knowledge is, we can just say that it's the belief, which is represented with the matrix. We can go back to the decision problem and talk about the restate it as given the robot belief and a collection of trajectories, choose the most informative one. And now we can understand why we want the most informative one, because the belief is a distribution and we want to make it to add more information to this distribution. And adding information meaning that we have less uncertainty in the distribution, and the trajectory that we choose will be the safest trajectory that we can take. Okay, information is measured usually using entropy. So we can define here this value function or objective function takes the current belief and the trajectory that we might want to take and give us the change in entropy if we choose to follow. And how do we calculate this objective function? For every candidate trajectory that we might have, right? We have these two trajectories. We will first predict which variables, or which factors we might add if we choose to follow this trajectory. We will incorporate them into the belief in order to get the posterior belief, and from this posterior belief, we will calculate how much information it has. And we will choose the belief that has the most information.
So the sample space is like a discretization of the space. What's the
Second?
distribution is on what? So the discretization of the space or what?
So it's not exactly discretization of the space, we discretize time. So we assume that the robot, for example, a control action takes 1 second, so you measure the state of the robot every once.
So the distribution over the state of the robots, the location and the time.
Yeah, so all of these nodes here, which are the locations of the robots at different time steps, and the locations of the landmark, which are static. This defines a state vector, and this is what we try to estimate. So we try to estimate the entire trajectory of the robot over time, not just the current pose. That's the difference between the filtering approach and the graph-based approach. We try to estimate the entire trajectory and the landmark. And the reason to do that is because we might have, here we can see this triangular shape. This is what we call a loop closure, which happens if in the previous state and the new state, I see the same landmark. So if I go around in a circle and go back to the same spot that I was at the beginning, that I can understand. If I can understand that, I can reduce the drift. That's the.
It seems like a huge space to me.
Right, thank you. That's a very challenging problem. This is exactly why it's challenging and why I want to contribute to this solution. It can grow to millions of states over time. Yes.
Still for larger number.
Okay, so this problem that we're seeing here on the graph can be represented in matrix form. Just as this problem, this is the initial belief, the square root matrix. Every candidate trajectory is represented with a stack of new Jacobian rows that we want to incorporate into this belief. We will incorporate each one of those blocks independently, calculate the posterior entropy, which is just the determinant of this matrix, and then we will choose the best one.
Is entropy normalized by the area covered? Maybe you can get more and more information about small area or explore new areas and get more information there.
Right, so it depends how many variables you have in the graph. So you can normalize according to how many variables you have in the graph. It depends exactly on the objective, but this is a little independent of the idea. Right, you can add normalization here on this function, but nevertheless, you need to update the matrix and calculate the term. You can also marginalize this matrix and find the uncertainty over just some of the variables. There are different approaches, but this is a little bit independent of what we want to focus on, which is how to perform this update efficiently, which is, again, I covered all the reasons why it's extremely computationally challenging. To evaluate the actions, we need to update the matrix. And as we said, this might be a very high dimensional matrix. And we need to do it for every candidate action. We want to do it online. Right? That's the key thing here. The robot operates, needs to choose its trajectory right now. This is an online problem. And our goal is try to take this problem and reduce the cost. So solve it.
So the bottleneck sounds like computing the determinant actually, right?
Second.
So the computing the determinant sounds like more of a bottleneck than updating.
So once you update the matrix and you have it in the triangular form, calculating the determinant is just a multiplication of the diagonal element. This is why we want it in the upper triangular form and not in the Jacobian form. Good question. Okay, so that's the problem. And the basic approach that we want to suggest here to improve the solution of this problem is use what we call simplified decision making, which means in very clear terms that we want to take the data structure that represents the initial belief, which in this case we know is the upper triangular matrix, and somehow simplify it in a way that will make all these updates that we need to perform computationally cheaper. Right, and then we will select the action based on this simplified problem, based on the simplified belief. And afterwards, we will go back to the original belief. And as we estimate, we will update the original belief. So we don't estimate the entire problem and sacrifice the estimation accuracy. We just use a simplified representation for planning, for decision making, and go back to the original. So we need to only perform one simplification, no matter how many candidates we have. And this idea is relevant for the other decision problems, not just this active SLAM. But in our case here, we want to simplify the square root matrix, the upper triangular matrix. Yeah, and this idea here is the reason why we use this idea is because it's independent of the planner. We can use there are different active SLAM planners that use different prediction models, that use different objective functions, as we said, but all of them at the bottom line need to update these matrices in order to update the belief. So this is what we focus on, and then you can benefit various algorithms, and we don't just specify a new customized algorithm. So this conveys a paradigm shift over the sense to impact. So instead of just having a single belief, single representation throughout the process that goes from sensing to planning, we now diverge and we have two different representations. One goes to the planner, which is a simplified representation, and one goes to the actor, this is the belief, the real belief that contains all the information in which we will continue to the next task. So it's actually a fundamental change to the autonomy paradigm. I'll just mention, I don't have time to go over it, but we didn't just suggest this idea. We provided a theoretical framework to support it. And this theoretical framework allows us to analyze simplification, to understand what's the effect of using a simplified belief over the action selection, and provide guarantees for the optimality of the problem. I just wanted to mention it. We don't have time to go over it, but it's just we back it up with some ideas and not just like stated that we should do it. All right. So how to perform this idea in practice? How should we simplify the belief? Since we know that the cost of updating the matrix depends on the number of non-zeros in the matrix or the density of the matrix, the way that we want to simplify it is by sparsifying it. So we want to have a matrix that has less elements in it, and then updating it will be cheaper. Right, so we provided a sparsification algorithm that takes as input a square root matrix that might be fully dense, so fully all these elements are non-zero, and will output a sparse approximation of it, specifically to be used for planning. And the key thing here, we don't need to understand the algorithm, but the key thing that we need to understand is that it relies on a selection of variables. We can select a subset of the variables, and these are the variables that we will sparsify from the belief, and this will determine how many elements here we remove from the belief. And notice that we don't just remove elements just like that from the matrix, because this might be compromise the belief. We do some compensation with the other elements for the information we remove. So which variables should we sparsify from the belief? We could use the theoretical framework that we suggested to understand that if we sparsify the uninvolved variables, then this will have guaranteed no effect on the quality of solution. Sparsify the uninvolved variables, which are all the variables simply that are not connected to any of the new factors, right? These are the new factors. These three variables here are not connected to any of them, so they are uninvolved. It's easy to identify. And if I sparsify those from the belief, it's guaranteed that I will not compromise the quality of solution. I can also sparsify the involved variables. In that case, I might have a loss in quality of solution, but I can still bound it using the theoretical framework. Right, so this is the original matrix. This is after partial sparsification. We can see that we have some empty rows here, and this is full sparsification. We have a diagonal matrix, which obviously will be much cheaper to update.
How do you calculate how good the specification is? What's the measure of this? What's the invariant you want to create?
So that's a part of the theoretical framework here. We define here the loss. The loss is the value of the real optimal action that I would have chosen solving the real problem, minus the value of the simplified action that I got by solving the simplified problem. So that's the trend of the objective function. And here, this is the real optimal action because it gives the maximal value. And here in the simplified problem, this is the optimal action that I identified, allegedly. Then the difference between the value of this problem and this value is the loss. This is what I had to pay for using a suboptimal action.
How is the function v defined?
V is the objective function.
It's linear, binomial.
So this is the same, this is the determinant of the matrix.
So you want to, okay, so that's the question. So you want to approximate the matrix and keep the determinant as little changes possible.
Right, so the V tells us how much information we have in the belief, right? That's, and the loss here is the difference between the information that I could have gotten to the information that I actually got. Let's move on and we can talk about it. So here's some of the experiments that we use to validate this approach. So this is a realistic gazebo simulator of a ground robot here. It has a LiDAR sensor on it. So as it goes around, you get cloud points measurements, and it goes around this indoor environment and tries to map it to gather information on it. And it solves sequentially active SLAM problems in order to solve this problem. Right? In each one of these planning sessions, we will examine 20 randomly generated trajectories because we said this is not the point of this contribution, but we'll create 20 randomly sampled trajectories to a certain point in space. And then we will try to choose the safest trajectory to this point in space, the one that will get us as most information when reaching the point. And this is how the problem looks like in the robot's view. We can see here the estimation of the map in blue. And this is where the robot is, this is where it wants to be, and we can see in different colors, different trajectories, and we try to choose the best one.
Okay. Just to follow up on Amir's question, so this loss function that we talked about, this value function, right? Like computing it, you don't actually compute it, right? The difference with the losses because it's like computing the real thing that you want to avoid. So what you actually computing the experiments, you bound it somehow, and
so that's what the theoretical framework allows us to do, to bound what the loss might be without actually explaining the real problem.
So can you say some few words about what you actually compute? Let's say just in the experiments, you don't compute the values, you compute something else.
No, in the experiments we compute the simplified values. Only the simple, we solve just a simplified problem. And then
I see.
And then you can get guarantees. What's the loss?
Taking into account the losses that your theory bounds, you just kind of retroactively bound it in theory.
Yeah,
I see.
So usually we perform some analytical evaluation of the simplification method and understand how it affects the belief, and then we can derive guarantees that are valid, and you don't have to actually calculate the real problem.
So I guess the more correct question would be, how do you choose which variables to specify in your experiments? Right.
So we said that if I choose the uninvolved variables, we proved that it will have no loss.
So you just to choose them, or
so we will see. Thank you for leading me to my next slide. We have for every planning session we solve 3 problems for comparison. One is the original problem. Of course, we just need to solve the one problem, but just for comparison, we solve 3 problems. One is the original problem with the real matrix. One with the partially specified matrix of the uninvolved variables, which we know we guaranteed theoretically, and we will verify here that it does not affect the quality of solution. And the diagonal matrix, in which we specify all the variables, and want to see what this extreme case will do. And this is the Jacobian rows corresponding to every one of these updates to every one of these trajectories. So these are the rows that we want to incorporate into this matrix in order to solve the problem. And this is the results that we got from the first planning session. This tells us the quality of solution. So we can see here the objective value for every candidate action. And the trend of this, maintaining the trend of this function tells us that we managed to maintain the quality of solution. So we can see here that the red and the blue, so the original problem and the partially specified problem exactly overlap. And this is what we could guarantee, and we confirm it here. And we can see that even the diagonal approximation, even though it's much cheaper to compute, it still maintains the trend pretty well. So in this case, we will choose the same action as the optimal action. We have no loss in quality of solution. And we can see here a comparison of the runtime of the original and simplified problems. And this, which you can see here, this little portion here, this is the cost of calculating the simplification. So the simplification is very easy, but it has a very significant effect on the solution time. And we perform.
So doesn't it mean that the graph has no, you don't use the graph eventually for this, for the choice of the next,
So the graph is encapsulated, represented with a matrix.
if you take a diagonal matrix, then you should simply discard the edges or.
Right, so we get, right.
This
So we
is
don't-
after the pure.
No, but it is, you're right, yes. Again, I have a whole other part of the talk and we need to go. We will get the belief with all the variables, but without the constraints. Yes, it will be marginalized, but I am running out of time, so let's move on and we'll keep the class on today. So we verified in other planning sessions, but we can see that these results are consistent. So in all of these problems, we maintain the trend of the objective function. We have no loss, and we still manage to reduce the quality, the computation time in the short. So that's obviously very effective. I will just really don't have time anymore to talk about this. We have a different approach that doesn't use specification, but use variable reordering. So just a change of representation without any approximation can get us similar results. And we can see here the accumulated planning time in the same scenario that we had before. We can see that this also helps us reduce the planning times.
So, how do the results presented depend on the noise level in the sense of
Again,
the results, the simplification that presented?
Yes.
How does it depend on the noise level? We would expect that if you have a lot of noise and the simplification is very costly.
so if I have a lot of noise, the cost of simplification is the same, but it will make the simplified version diverge more from the original version. The more uncertainty you have, the more they will diverge.
But we would still expect that the two-sparse approximation still fair well.
So that's why I'm saying it will diverge more and more. So the higher the uncertainty level, the green line will diverge more from the, or will be less consistent with the original. Okay, some potential extensions of this project, we can have different simplification models, methods. We can extend the theoretical framework to allow us to provide guarantees in more complicated scenarios and maybe compose simplifications. And the most interesting one is that we might be able to use deep learning or statistical machine learning to learn how to simplify problems or how to simplify beliefs instead of calculating this algorithm. Okay, this concludes the first part. I hope I will not be over time, but this concludes the first part. And now we'll move on to the second part, which is my postdoc work. This was my PhD work. This is the postdoc work. And we'll talk about a completely different problem, still under the planning umbrella, which still wants to contribute to increasing the scalability of the planning problem, but in a different plan. And we'll see here two problems. And the reason for that is because our contribution is easier to understand first in a simple problem, and then we'll move on to a more realistic problem. So let's start with a simple path planning problem in which we have this grid, which specify the planning domain. Planning domain specify the state space, which is called collision-free positions on this grid. And we have a start state and a goal region. We want to find the task planning problem is to find a collision-free path over this grid from the start state to the goal region. Right, and the action space is we can go left and right and up and down, and transitions are accordingly. So this is a path planning problem, but it's formulated as a task planning problem. Task planning problem meaning that we plan in a discrete symbolic domain. Right, we have symbolic actions, go up, go down, go left, go right. This is symbolic problem. And task planning problem, so this is how a solution to this problem would look like. A sequence of actions that lead from start to goal. And this is one instance of a task planning problem, but task planning in general, that is sometimes called AI planning or automated planning, is one of the most fundamental problems in AI. Since the 70s, since even before that, it's been the interest of the community. Still to this day, every year we have a planning competition of ICAPs, of people trying to suggest new planners to solve task planning problems. In the competition, we give them some task planning problem that is a surprise, and their planner needs to be able to solve this. So this is still a very active area of research. And we want to, with our approach, just like we did beforehand, to give some conceptual domain agnostic approach that will allow us to benefit existing planners instead of giving a new specified plan. So the desired paradigm that we want to use to benefit the planning problem here is to have something that looks like this, to allow the planner to improve from its experience. So we have plan, act, sense, and then we can understand the results of my actions, and if it's good, I can make a conclusion, improve, and then plan better the next time. The question, of course, is how to do it. So we might consider some learning from experience approaches, which this is very popular these days, using deep reinforcement learning. Right? This is a very popular approach, but we know that this is not suitable for the type of approach that we're trying to have. Right? This is not suitable for lifelong learning. First of all, it's an offline process, usually, which it's not clear how to automate it. Usually we learn a policy using reinforcement learning before we deploy the robot, and then we allow it to use the policy online. Right? We also need numerous examples in order to learn each policy. It's struggles with task planning problems that are non-monotonic, and usually this is coupled with a specific problem. So instead of using deep reinforcement learning or policy learning, we're trying to rely on a very simple approach, which is called instance-based learning, which in simple words means that once I solve the problem, I will cache in some way this solution in my solution library. And if I have a new problem, I will see, can I somehow match this successful solution to this problem? And if it matches, then I will try to reuse the solution instead of solving from scratch. And this requires only a few examples, individual examples. It's very explainable because I can tell why I'm planning, and it supports continual online improvement and learning. So now the question, of course, is how can I encode the solution effectively so I can reuse it? One of the most common approaches is using what we call macro actions, which are just successful sequences of actions that I've seen that they work, and I want to cache them in my library. And the advantage, so we can see here a planning problem that we managed to solve. We can see here the action sequence from start to goal, and I will cache this action sequence as it is. And the advantage of actions is that they are portable, meaning we can apply actions from different states. So if here my start and goal moved, I can still apply the same action sequence, and it will still lead from start to goal. So that's a successful generalization. But on the other hand, macro actions are very fragile, because if here I added a little obstacle part, and now this blocks one of the actions, it's unfeasible, then this compromises the entire plan, and I cannot be used. So that's a failed generalization case. So maybe we can try to do something else and start learning macro actions. Maybe we can try to cache state roadmaps. What is a roadmap? Assuming here that that's the same problem that we had before, I can identify key states over this trajectory that I've passed through, and I will just save this sequence of states, which we call the roadmap. And next time I have a problem, I will try to go through the steps again, through this sub goals again, in order to solve my new problem. And this is, as we can see, it's less fragile because here, now that I have this obstacle, because I don't confine the actions, I can just go around the obstacles and overcome this part, right? While still benefiting from the previous solution. But we can see here that if we lose the portability of actions, if we rely on states, because now if we move the start and goal, this no longer leads from the start to goal, this roadmap. So we lose the portability. So can we have a solution that allows to perform to generalize to both cases? And this is what we suggest. The answer is yes, we can, and this is what we suggest. Caching an abstract roadmap. What is an abstract roadmap? Abstract roadmap represents a dynamic two-stage transfer. The first part happens when I solve the problem, so that's the same problem that I solved. And now I have the same states here that I identified. Instead of just caching them as they are as positions on the grid, I will first project this sequence of state into some compact topological primitive. So we can see here that if I take these states, I can just compact them into this shape, and this represents my abstract roadmap. So this happens when I solve the problem. Now, if I have a new problem, I try to see if I can take this shape, this primitive, and somehow stretch it and place it somewhere on the grid such that it leads from the start to goal and solve the problem. So we can see here that this allows to generalize to both cases. This is the same roadmap that we had before. It leads from start to goal, right? We can overcome this part here. And here, even though I move the start and goal, I could reposition the roadmap and stretch it a little bit or compact it a little bit such that it can fit here. So I could generalize to both cases.
And we try to fit this stretch it. Do you have the full information about the new environment that you try to adapt it to?
Yeah, I should have clarified. We don't have uncertainty here. Don't have it. But we don't explicitly know the entire environment. We need to query what happens in which image state. But you can know if it's a collision or not a collision.
How do you choose the states along the roadmap?
We will talk about it in a little. But that's just tells us how we can generalize and why this approach generalizes better than any existing approach that it might be, either state roadmaps or map directions.
Just a lot of computational complexity of it, because you're trying to find a subgraph, a fixed subgraph inside a given graph. This seems like a very complex problem, right?
We don't. Why do we have a graph? This is just
1, 2, 3, 4, 5. It's a graph, right?
right, but it's a linear graph, right? We have a lot of states here, and we're looking for key states in this.
This is because it's very simple. Like if I'm giving you a very complicated graph.
But it's notice that it's learned from the execution. The execution is by definition a linear graph, because it's take a state, apply an action, a state and action. It's not from the planning graph. It's from the solution. Yes.
Okay. Yeah.
So that's a linear graph, and we will identify the key states on this execution. So we can concretize the idea that we had before, wanted to improve, and now we can see that after solving a problem, we will try to extract an abstract roadmap, and we'll talk a little bit exactly how to do it. And then next time I plan considering all the abstract roadmaps that I have in my library and try to solve them. And just theoretical intuition why this helps us reducing the planning cost. So this is the same problem if we were to solve it naively, and if we were to solve it after we manage to match a roadmap. And we can see that matching a roadmap allows us to decompose this problem dynamically into the dynamically defined subtasks, which we would just use the same planner that we had before to solve it. So I have some planner X, instead of just running it from start to goal, I will run it on over this local subproblems here to plan from here to here, from here to here, and so on. So this approach just allows us to decompose problems, and we can use the same planner that we had before. And because task planning is usually exponential in complexity, or at least superlinear, then it means that solving k smaller problems is better than solving one big problem. And this is why it helps us reduce the cost of solutions. And we can also solve them in parallel in many cases. So we can see here, this is just a depiction of running A star to solve this problem with and without a roadmap. So we can see that we start expanding more and more nodes. And here I already managed to solve the problem. And here I will still have to expand more and more nodes until I found the solution. So we also verified it with some experiments. So these are some tasks, some problems with different topologies that we want to see how they will benefit from using roadmaps from this library. We can see that in these three cases, I don't know if you can see the colors, we have some overlay because we managed to match a roadmap to the problem. And in this case, we did not manage to match the roadmap. And see the results of planning. Just running a simple A-star planning. We can see the results of the baseline versus using the decomposition with the roadmap. This is orders of magnitude reduction because of the exponential growth of the problem. And we can see in the final problem where we did not manage to match the roadmap, the attempt to match, and we'll talk in a little bit exactly how we try to match, is so insignificant compared to the planning cost that we didn't really pay anything for trying. But if this attempt was successful, then we can benefit from it.
So did you submit this to the competition?
Not yet. Not yet, but maybe soon. We're trying to robustify some of the experiments. Okay, so this was the first problem, pathfinding. You know, one is take this idea and try to generalize it into a more realistic robotic case, which for the task of object rearrangement, in which we have a robot, and it has here a tower of blocks, for example, or it can be any other items. We want to reconfigure them to a different shape. And here, this is like a towers of Hanoi problem. We want to reconfigure them to the other side of the table in different order. Right? But it can be any manipulation of objects. And we want to see how this approach can generalize to this case, and also how can we automate this in this case. And this will allow us, for example, to generalize if we manage to solve one tower problem. We can, now that we have distracting objects and maybe we change the blocks to different colors, how can we use this solution to solve this problem? And maybe if we have multiple blocks, multiple towers, how can we generalize to this case? So this problem actually is quite hard, and it encapsulates multiple planning layers. One of them is logical reasoning. Then we have the task level, which is discrete planning like we had before. Now the actions are maybe pick a block, place a block on the table or another block. And then we have the motion level, which is the continuous how to move the robot. And we will focus on the task planning level, even though theoretically this approach can fit and benefit each one of these layers, but we'll focus on the task planning part of this bigger problem. So usually this is task planning problems are specified with PDDL, which is the planning domain definition language. This is just a specification language in order to specify task planning problems. For example, in the planning competition, all the problems are given in PDDL. And it's actually very simple. We can define here the blocks world domain. And we can see here that we just define the object. So we have a symbol for block A, block B, block C. And then the initial state is some propositions over this symbol. So block A, block C is on the table, block A is on block B, and so on. Block A is clear, so there's nothing on top of it. And the goal state is also some propositions that we want to satisfy. We want block A to be on block B and block B to be on block C. All right, so this is how we define the problem, define the domain. And how do we generalize to this case of PDDL? Where beforehand, when we looked about planning over the graph, over the grid world, the abstract roadmap existed in the same domain, existed in the same state space. It was still on the grid, just more compact. In the more general case, the abstract roadmap, the state of the abstract roadmap needs to live in a different state space, in an abstract state space. This is why we call it an abstract roadmap. So beforehand, we could just compact the states, and now we need to move them into a different domain. We want to open the door, it's been a little hot with the sun. So how to do this mapping of roadmaps from the original domain into the abstract domain? We can use what we call an abstraction key, which is the computational tool that we use to map roadmap between where it first existed on the grid into this abstract domain. And it just comprises of a projection function that takes a state into an abstract state, and a reconstruction function that takes the abstract state and return state, and it relies on a parameter. And very intuitively, we can think that the parameter is some property of the state. Reflection removes this property from the state, and reconstruction puts it back in the state. And different properties work on different properties that allow us to remove different properties from the state. So how will this look like? You can see here a circle. This just represents a state, a propositional state. Every wedge here might be a proposition. So we can see here that we have a proposition that maybe specifies the color of a block. And we can, with projection, remove this reference to the symbol. And now we have an abstract state that does not specify colors. And now if I want to reconstruct it, I can reconstruct it with a different color, and I can change the color to red. So instead of directly mapping from blue to red, I just remove the color and then I can replace it with a different color. And of course, I can do it if I have a sequence, if I have a roadmap, a sequence of states, I can do all the projection to all these states, get this abstract roadmap that lives in an abstract state space that doesn't have colors anymore. And now if I have a new problem, I can try to reconstruct it by adding the right colors. Right, and the parameter that I would choose is the invariant property, something that doesn't change and exists in all states. So we can see here, so this is the same thing that we just saw in the previous slide. This is what we call symbols. If I have a symbol that repeats in all states, I just remove it, and it doesn't exist here, and then I can replace it with something else. Here, a different example, which we call attention, in which if I have propositions that don't change, for example, if I have blocks that don't change their location throughout the plan, then I can just ignore them, and I'll have a substate here, and then I can replace it with something else. And actually, also the problem that we had before, the geometric case can also be specified with an abstraction key, which with projection we will compact the roadmap, and with reconstruction we will stretch. So now that we understand that we can do this transfer using abstraction keys, we can restate the concept. The first part happens once we solve the problem. We'll extract the roadmap by projecting it using some abstraction key to catch this abstract roadmap. This represents in my library some skill that I can then use to solve new problems. And then when I have a new problem, I'll try to reconstruct and match it to a new problem. And if this match is successful, then I will just follow the actions. We'll follow this rule. So just briefly to mention that these two components, the skill extraction, which is what we said, identifying the key states, and the skill matching, both of them can be performed automatically. This is what the abstraction key gives us. So we can see here that for every abstraction key, we can measure, we can define some information measure, which, for example, for symbol stripping is how many symbols we have in the states. For attention is how many propositions we have in the states. And then we can reason about segments of these executions and see how much information they have, and reason about the abstraction score. The abstraction score is how much they have in common that I can remove from this segment. So here we see that this segment have a lot in common. So I can, because all of these three properties are the same, so I have a lot to remove here. So this has a high abstraction score. And by reasoning about abstraction score, I can define this as an optimization problem to maximize the sum of abstraction scores per segment. So then I can take this long execution and break it down into segment such that the sum of abstraction scores is maximum. And this is how I identify the key states in the roadmap that I will then abstract. And I can extract a skill from each one of these segments and also from this skeleton skill states that we have.
Will approaches
Yes. So this is to say that extraction can be automatically solved because it's an optimization problem. This is also valid for the geometric case. Skill matching can also be automatically solved because this is simply a constraint satisfaction problem. We'll see if we can map the roadmap to our starting goal. If we can do so, then it's a match. So that's a constraint satisfaction problem. This can also be automatically solved. And if we manage to do it, then we can reconstruct the roadmap and solve the problem. And we can also, we'll not talk about it, but we can sequence also multiple of this roadmap to solve longer problems. So this is just experimental results. We solved this object rearrangement problem. So we began by solving 10 randomly generated one-tower rearrangement problems. We solved them using standard planner, and we used these solutions to execute skills. And we cached them in the library. And then we solved batches of 50 new problems for 2 towers, 3 towers, and 4 towers. So we increased in difficulty. And then we tried to solve this problem with the skills that we learned and without the skills. And we used the state-of-the-art task planner. It's called Fast Downward, or FD. This is currently the best you can get with. And this is the results that we have. This is the median planning times for 1 tower problems, 2 tower, and so on. We can see that for 1 tower problems, actually FD performed better than us because it didn't have to manage skills and all that. But because the complexity of the problem grows exponentially, you can see that quickly FD starts exploding. Even though we talk about 2 towers, people might think that this is an easy problem. This is not an easy problem for robotics. This is state of the art, already explodes in timeout in most of these problems. It cannot rearrange 4 towers. And with our solution, we managed to modularize the problem, and we scale a lot better, right? So we can see here 2 seconds compared to 43 seconds, and so on. I think that we finally also explode at 4 towers, but we scale a lot better with the same plan. So we managed to solve problems that are not solvable with state of the art by using this basic automatic technique. And we can have some extensions for this to use it in different domains, to have different abstraction keys. And like I said before, maybe we can use machine learning to learn abstraction keys that allow us to generalize in more cases. And this concludes here the second part. I will just mention that my greater vision for my research is going beyond planning and actually provide the algorithmic foundations for robotic cognition and everything that it encapsulates. And I have done a lot of thinking about it, and I identified some points that I think should guide this research journey. I will just mention a few. One, that it takes a lifetime to get cognition. Humans don't get cognitive ability as they are born, but they learn as they operate and they improve, just like we did with this last project. And maybe we can have robots have the same thing. We can maybe automate computational cognitive processes like the simplification of problems, like decomposition of hard problems to small problems, and so on, that they are not tied to a specific problem, but they are general. We can rely on memories, which are like the skills. We can have explicit references to our past experiences. Neurosymbolic AI, which is the combination of machine learning algorithms, statistical machine learning with this symbolic algorithms. We need to understand how to combine them effectively. And if we do it, then we can have verifiable robots, meaning that we can build trust in the system as a whole, and not just in specific algorithm, but we can trust a robot and maybe put us in general play cards. And with that, I would like to thank my advisors, which have already did their tracking, the Engelman, the collaborators, and all of them for listening.
Thank you very much, Ben. Let's